discuss one very important topic of the electronic devices, which is basically just the characterization of the particular semiconductor. Okay, firstly I am discussing the general classification of the semiconductor. If that is a semiconductor, the first classification is about to purity of the semiconductor. That means in the basis of the purity. And in the basis of the purity, semiconductor can be of three types. The first one is pure semiconductor. Second one is intrinsic semiconductor. And the third one is extrinsic semiconductor. This is in the basis of the purity of semiconductor. Now, the second type of characteristic is elemental semiconductor, and the second variety is compound semiconductor. And all these characterization or the classification of the semiconductor already we have discussed. Okay, we will not discuss these type of characteristic of the semiconductor. Today I am discussing the new classification of the semiconductor in the mechanism of the recombination. We know that if at any particular semiconductor, at any particular temperature, some generation of the electron hole pair and the recombination of hole pair will exist. Now, one variety of the semiconductor will also exist in the manner of the recombination. How the recombination will take place into the semiconductor. So, firstly, I am doing the general discussion. The energy band diagram, the basic, all of you know that it is a EC and it is a EV. If I will provide any particular energy to this, what will happen? One electron will get excited from here to here, and this much energy is required to pump, to detach the electron from the valence band and to transfer into the conduction band. Whenever this will occur, here one hole will exist and one electron will come here. And energy required to provide this is, I am saying, E is equals to H nu. That means if this one photonic energy you will provide, and if this energy is enough to detach this electron, that is known as EG, the forbidden energy gap. That means if the energy, whatever you are providing, it is sufficient enough to detach the electron and hole pair, then the electron will go from valence band to conduction band. And this process is known as EHP generation. Now, any particle cannot exist in the higher energy level for infinite value of time. Because it is a general rule of the nature, each and every particle will try to achieve the lowest energy state possible. Okay, that is the reason why if you will throw the ball, and after some time again the ball will come to the ground location. Because whenever you are providing the energy to the ball, that is going to some height and again it is coming to zero level. That means each and every law is valid each and every physical situations. The same thing will happen here. At the EC, definitely the energy level is high. So whenever this will release the energy and it will again come to this location from EC to EV, this process is known as the recombination. And if it is coming from here to here, definitely the energy conservation will come into the picture. Energy can never be created nor be destroyed. So if it is losing the energy from here to here, definitely it will release the energy. And that is H nu. Whatever the energy have pumped from here, that must have to get extracted from here. Then only the energy conservation will get hold. Now what is happening here? We have to describe the semiconductor now in the terms of the recombination. How many type of recombination can exist there? Okay. So this is a basic idea which we will discuss in further discussions. I am not interested in the generation part, I am interested only in the recombination part. And after the completion of this particular aspect, you will see where you can use this, and most of the time you are using this. Now, all of us, we know whenever the electron and hole will travel along any particular distance, that will carry some velocity and it will have its mass also. And whenever I will take that particle as a particle, that electron as a particle, then the mass is m and velocity is v, and the momentum will be p equals to mv. And all these things, whatever I have recombination generation, we are going so much in the detailed discussion of that whenever the size of the electron is very less. So whenever you are continuously decreasing the size of your interest, the particle will become the wave natures. The particle will become a wave. So whatever the discussion we are doing here with the particle nature, we have to see the aspect of the wave nature also. So if the k is the quantum number, then the quantum momentum, this is a classical momentum. That means these numbers are coming with the classical mechanics, and these quantum numbers and the Planck constant, these things are coming from the quantum mechanics. So that momentum will become hk. And this hk is nothing just the quantum momentum, where this is a particle or the classical momentum. So here we are discussing in the size of the electron, and electronic size is very less. So this particular momentum does not have any meaning for me. Okay, we know one relation, E is equals to P square divided by 2m. As I will put here, you will get h square k square divided by 2m. Now from here we can say that the energy of the electron and the momentum of the electron is having the parabolic relation, or in other words, E is equals to any constant A k square, and it is the equation of the parabola. Okay, whenever we will plot these things into one plane where the k is my independent variable and energy is my dependent variable, because in entire energy band diagram we have discussed that energy always will be in vertical axis and all the remaining things will be in horizontal axis. So here also we will enhance this particular diagram, and that diagram is known as EK diagram. That means energy versus momentum. Little bit later you will see what is the importance of this to describe the recombinations. So whenever we will discuss this, I will tell that this axis is E and this momentum is K. Okay, so whatever the diagram you will draw here, that is known as the EK diagram. Now as we have seen that the E is equals to some constant A into K square. That means the momentum and energy is having the parabolic relation. So this energy will be different for hole, and this energy will be different for electrons also. And if the energy is different for electron, definitely the momentum of the electron will be different, and the momentum of the hole also will be different. So I am saying that this is the level of EV and this is the level of EC. So now I am interested in one point, that up to now whatever the energy diagram you have studied, you are just simply making this, and you are saying that electron is moving from here and again it will go from here to here. You are not interested what is the momentum of the particle. Okay, but in the recombination process, you know that if you want the recombination of electron and hole, the momentum of the particle must have to be constant, must have to be same, otherwise the recombination will never take place. Okay, so there are two possibilities. The first one, that electron in the conduction band and the hole in the valence band is having the same momentum. And the second thing, they will not be same. So we will try to characterize this into two types in the basis of the recombination. So firstly, I am discussing, you have seen that the energy and the momentum is having the parabolic relation. So I am saying this like this. This is the EK diagram, energy of the hole in the valence band. Similarly, you will see the EK diagram. That means the energy versus momentum of the electron in the conduction band. And least value of this is known as EC, and most value of this is known as the EV. It will touch this. Okay, and the maximum value is nothing, that this is a EV and this is a EC. And if I will say, this is a K1, the momentum of this particle, electron at this moment, and it is a momentum K2. But you know that to occur the recombination, electron momentum and the hole momentum must have to be same. Must have to be same means either this electron will come here to here, or this hole will go to here to here. Anything can possible. But what will we do? We know that the mobility of the hole is very less, so it cannot move very frequently. Definitely electron will move. So what will we do? We will try to match the momentum of this electron and momentum of this hole. Okay? Then what will happen in many of the semiconductor? What is happening there? Some of the trapped energy states will be there in any particular semiconductor, which will act as a recombination agent. What the recombination agent is doing? They are just trying to hold the electron for some time for any particular hole to make the recombination possible. That means if the electron momentum is this, it will try to make the momentum equal of this electron and momentum equal of this hole. Then those energy states are known as the trapped energy state. Meaning is very simple, that these trapped energy states are nothing, just the energy levels which will hold the electron or the hole for some time, by which they are trying to make the momentum equal of those two particles. So how the transition will take place? The transition like this. Now it will come here. Now see, the momentum of this particle and momentum of this particle will be same, because they are exactly coming to K2. This transition from this point to this point, here the momentum is K1 and here the momentum is K2. Okay, if electron is falling from conduction band to hole in the valence band, whenever it will come there, definitely the momentum must have to be constant of both the particle. Otherwise this recombination will not take place. Yes or no? This type of semiconductor, where the transition of the electron from the conduction band is not happening directly to the hole location. Now see, it is coming from here to internal energy state, and then from internal energy state to this state it is coming. Whenever this type of transition will occur in the recombination process, then this type of semiconductor is known as indirect band gap. Indirect band gap semiconductor. Because the transition along the band gap is not occurring directly. Electron must have to attain some any other energy level, and then from there it will come to the hole location. What is the problem here? Whenever it will get trapped, definitely the velocity of the electron will get changed. And if the velocity is getting changed, definitely the momentum of the particle will get changed. And if the momentum of the particle is getting changed, what is the meaning of that? If the velocity is getting reduced, definitely the lifetime of the charged particle will be high. Yes or no? And if the lifetime of the particle is high, the recombination will take little bit later. If the recombination is taking little bit later, definitely those devices will become sluggish. Okay? And that is why you know these type of properties you will see in the material of the elemental semiconductor. Okay, this type of, and if it is losing the energy from here to here and from here to here, definitely it will emit the energy. Okay, and this number I will come little bit later, but definitely in the recombination some energy will get released, and in the generation some energy will get absorbed. Okay, so whenever this type of phenomena will occur, that electron is not coming directly from this level to this level, that is known as indirect band gap semiconductor. Okay, and example of such type of elemental semiconductors like as a silicon and germanium. These are the elemental semiconductor. That means here we have studied that electron and hole is not having the same momentum. What will happen if the electron and hole will get the same momentum? Same momentum means like this. The hole here and the electron here. If the electron is here and hole is here, both are having the same momentum. Then what will happen? Directly electron will come from here to here. So I am just showing here the transition of the electron from conduction band to valence band directly in this particular situation. Yes or no? This is only the difference. Whenever the electron is directly coming from the conduction band to valence band directly at the position of the hole, that is known as the direct band gap. Direct band gap semiconductor. And if it is coming from this energy level to this energy level, that means it will release the energy. Definitely this energy is h nu. Here also h nu is emitted by this particular semiconductor. Here also the energy will get released by this particular semiconductor. Now, we know two things. Energy, whenever you are providing, in which form of energy you can get the energy? The first one is thermal. That is the reason why if you will use any particular semiconductor, that is getting heated up. Yes or no? So first energy which you can get, that is a thermal energy. And the second one is spark or light. That is known as photonic energy. Now, depending on the material, these things will get decided. Okay? Because what is E? E is equals to h nu. And we know that what is a nu? Frequency of any particular wave. Hc by lambda. Now you know that this lambda is a constant value for any particular light, where this E is the energy dissipated by any particular photon. That means energy released by any particular photon. And this energy gap is fixed for each and every material. If this is fixed, then this will be fixed and the light radiated from that will be fixed. Yes or no? So, elemental semiconductors, silicon and germanium, are coming on the invisible range. If you will calculate this, the lambda Hc divided by E, where I will put this E value, if that is a silicon, you will put Hc divided by 1.1 Eg. Whenever you will calculate the value of the lambda from here, that will come in the IR range. That means the emitted light from this particular photon will be in IR range. Okay? But whenever you will take this type of material, examples of this type of materials are compound semiconductor. Example is gallium arsenide. It is the most general example. And what is the general band gap of this? General band gap of this material is 1.42 electron volt. So if you, instead of 1.1 electron volt, if you will put this, then you will see that lambda, whatever you are getting from here, the lambda is equals to Hc divided by 1.24. Sorry, not 1. 1.42. Whenever you will see from here, then you will see this is nothing. This lambda will occur in the range of visible lights. Instead of IR, you will get the photon of the visible light range. Okay, so this photon, if this is a direct band gap material, then this will be in visible range. Okay, so that means whenever you will use this particular material, it will provide the light in the visible range, and this particular material will provide the light in IR range. Now see the application where you can use this, or in other words, where you are using these things daily. Okay, firstly I will come to this. What is happening here is basically, you are providing some supply, yes or no, and what is this basically? The electron is coming from here to here. It is just the current. Because of the current flow in any particular semiconductor, you are getting the emission of the light. Yes or no? So, whenever the light is coming, that means you can use as a transmitter or as your signal. Yes or no? And such type of application, where you are using such type of applications, the very famous device where you are using this property of the semiconductor, direct band gap or indirect band gap, that is known as light emitting diode. So that means these two type of component will be decided according to your application, where you want the light signal in the visible range or the light signal in the invisible range. Invisible means IR range. Okay, according to your application, you will choose the material, whether that is a semiconductor or elemental semiconductor, silicon or germanium, or the compound semiconductor, gallium arsenide. You know that whenever you will use the gallium arsenide, this will provide the range in the visible range, and whenever you will use this, this will provide in the IR range. Now, all of you are using the TV remote. In remote, you can see one bulb type of thing is there. Whenever you are pressing the button, it is releasing the signal from there. And that is, you cannot see that particular light. That is invisible range, IR. Okay, so that bulb is nothing, that is just the LED, where such type of material you are using. Okay, that means in TV remote you are using the LED, and which is basically the material silicon. Because that emitted light in the range of the invisible range, IR range you are using. Are you able to see the signal of the remote? No, because that emitted signal, that emitted light in the invisible range. Now, see the traffic signals. What is happening there? In the traffic signals, you are getting the red color and red color, green color, or yellow color, according to their traffic controls. Yes or no? That means there also you are having the bulbs. Those bulbs are not basically the bulbs, those are LEDs which are providing the light in the visible range. And according to this selection of the material, you can change this particular E, and if you can change E, this H and C will be constant. That means if you are able to change this E, band gap of the material, you can change the color offered by the particular material. And this is the reason why you are using the compound semiconductor or the direct band gap semiconductor to make the LED in the visible light range. So in the traffic signal also you are using the LED, and in the TV remote controller also you are using the LED. But now, just because of the material, you are not getting light in one side and you are getting the light, visible light in the one side. So whenever you will use the IR remote controller, you will use the silicon. If you are interested in the visible light range, that means traffic signals, you will use the gallium arsenide. Now see the use of this particular semiconductor. Why the compound semiconductor are so much popular in the direct band gap, are very familiar to make the LEDs. If you are having the elemental semiconductor, what is the beauty of the elemental semiconductor? You cannot change the energy band gap of the material at any particular temperature. If the temperature is fixed, you cannot change the energy band gap of silicon or germanium. If that is the silicon at room temperature, that will be 1.1 electron volt. If that is the germanium, that will be 0.7 electron volt. You cannot change that at any particular temperature. But what is the beauty of the compound semiconductor? This is basically the 1 mole. Yes or no? So, the general representation of this is gallium of X and arsenic of 1 minus X. This is the mole fraction of the gallium and it is a mole fraction of arsenic. Okay. Now, if you will change the value of this X, the component of the gallium and arsenide, the mole fraction of the gallium and arsenide will change. According to that, you can change the band gap of the material. That is the beauty of the compound semiconductors or the direct band gap semiconductors. If you are able to change the energy band gap of the material, you can change the color offered by the device. Okay? Because the energy band gap is directly related to the wavelength of the emitted light. If you are able to control the wavelength, you are able to control the color also. Okay, that is only the difference between the direct band gap semiconductor and the indirect band gap semiconductor. Direct band gap semiconductor will provide you the light in the visible range. That is why you are using that in the LED in the traffic signals. And the indirect band gap will also provide the light which will be in invisible range or in the infrared range, which you are using in TV remote control or AC remote control. And it's all about the indirect band gap and direct band gap semiconductor.